next thing would be quasi-static process. Now this quasi-static word is comprised of two other words. One is quasi and one is static. Now what does quasi means? Quasi means almost, and static means static or equilibrium. That means by combining these two words we get a word called almost equilibrium. Okay, now we have divided this board into two equal set of diagrams. In one we have discussed about a normal process, and in the second diagram we have discussed about the quasi-static process. So to make this better understand, let us discuss these diagrams. So normal process, what happens? Suppose there is a piston cylinder arrangement, there is a system, suppose a mixture of air or some simple air, pressurized, which is pressurized, and we have put on some weight here, so that the piston comes down and balances this pressure. Okay, and here there are two stoppers. Stopper means these things will stop this piston to go out of the cylinder. Okay, in next diagram, what happens? If you remove this weight, this pressure, this unbalanced pressure will try to move this piston upwards. Okay, and it will just start into these stoppers. So in this process, what happens? We are directly getting stage 1 to stage 2. We do not know the path. That's why I have kept from 1 to 2 this place blank. Okay, so this is the process. Now the same thing happens in quasi-static process, but here what we do, we have also taken the same block of weight W. We have also taken the same block, but now we have divided this block into number of parts. Okay, now in this part, what happens? If we take out one of these pieces, suppose if we take out the first piece, what happens? Now this piston, to balance the pressure, unbalanced pressure inside it, it will go up a little bit. Okay, now in this way, if we try to remove once a small piece of weight once in a while, then what happens? It will pass through a series of equilibrium processes, system. Now this process, I will say that it is in equilibrium state. That means in a state. Last video we have discussed about the state. So what does a state means? That means it is not going to change the process now. Now what happens? If we remove one of the piece, to make it equilibrium, this unbalanced pressure will try to push this piston a little bit. Okay, like this. If you take out one of the pieces once at a time, then it will pass through a number of equilibrium states. So I have drawn it here. Suppose from stage 1 to stage 2 you want to go, by pulling up a piece of this weight, then it will pass through a series of equilibrium process, and it is going to be extremely slow process. Okay, so the same thing we do it in a completely slow manner, once in a while, passing this step 1 to step 2 through a series of equilibrium states. Then this process is named as quasi-static process. Okay, we have discussed quasi-static process. Now in this we are going to reverse the quasi-static process. That means in quasi-static process, what we have discussed, that we have come from state 1 to state 2. By removing one of the small pieces once at a time, we have come from stage 1 to state 2 by passing through a number of equilibrium states. Now in this case we are going to reverse this. That means we will go from state 2 to state 1 by adding the pieces of weights one by one. Okay, in stage 1 what happens? The piston is directly in contact with the stoppers. That means this piston is stopped here to balance the unbalanced pressure here. Now what will happen if we reverse this? We will take one of the pieces of these weights once at a time. So in first stage, that means in second stage, what we have done, we have taken one of the pieces back on the piston. Now to balance this piston will come down a little bit. In the third stage, what happens? We have taken another piece and put it back again on the system. Now this unbalanced weight will make this piston to come down. Like this, if we add once at a time each of the pieces of that weight, it will finally go to stage 1 through this number of equilibrium states. It means this is going to be one equilibrium state, this is going to be an equilibrium state. Like this, it will go back to the stage 1 which we have taken in the quasi-static process as stage 1. Okay. Now from this process we can say that this process is reversible. That means like the way it has come from state 1 to state 2, in the same path it has gone back to state 2 to state 1. So maybe we can call this reversible, but there is a condition. To be reversible, it must be frictionless, because due to friction energy is lost both the time from state 1 to state 2 or state 2 to state 1. It's not like that from state 1 to state 2 due to friction some energy is lost, so while going back due to this friction this energy will be gained back. It's not like that. In both the cases friction will be lost. For friction some energy will be lost. Okay, so to be reversible these processes has to be frictionless. Okay, so you can make this statement easily now. Quasi-static plus frictionless is going to give you a reversible process. And from this equation, I will call this an equation. So from this equation we can conclude another thing, that all quasi-static processes are not reversible, but all reversible processes are quasi-static processes. That means to be quasi-static, to be a quasi-static process, this may be a reversible process or maybe not, but to be a reversible you have to take these two in consideration. To be reversible, quasi-static is a must option. Okay, quasi-static must be there, but to be quasi-static, if I remove the frictionless, that means if I give friction, this quasi-static process also will become an irreversible process. Okay. Okay, the next thing would be thermodynamic cycle. Now what is a thermodynamic cycle? A system is said to have undergone a thermodynamic cycle if the initial and final state of a system is going to be identical, then only we call it as a cycle. Now from this diagram, if we think that in initial condition the system is in state 1 and up to state 1 to state 2 it has changed, that means a process has been there from 1 to 2, and from process 2 again in another path it has come back to the same initial position, then we will call that the process 1 2 and 2 1 has constituted a cycle. Now to be a exact definition, we must say that to produce a cycle there must be a series of processes. Now that series may contain 2 processes, 3 processes or hundreds of processes. The main motto should be that we should return back to our initial position. Okay, so this is going to be a cycle. So in this diagram 1 2 2 1 is also a cycle, 1 2 3 1 is also a cycle, because in both the cases it has returned to state 1. Okay, now another thing we need to remember here, that in a cycle the change in properties is going to be 0. Now in the definition of properties, one thing we have discussed, that the properties in a certain state has a definite value. Okay, every property is going to have a definite value for a certain state. Now if this 1.1 is a state and 0.2 is a state, then properties are going to be different for these two cases. But whatever path you take, whether you take this path and come back to another path, or you take this path, go back to this path and come back to this path, then the properties whichever whatever the properties were previously there in state 1, the same property will regain their value when it comes back to state 1. Okay, for a particular point the properties are going to be same. So in a cycle, as always the system comes back to the initial point, that's why the change in the properties is not there. Okay, the values of these properties are going to be same. Now another thing we need to know here, that they produce a cycle, you need to have at least 2 processes. Okay, at least 2 processes must be there. Okay, otherwise there will not be any change of state. If we take a one cycle, then this has gone and come back to here, then this is not a process, because as the definition of process we have learned that process is a change of state, but here it has begun from state 1 and already come back to state 1 without having any intermediate state. Okay, that's why only a single process cannot be considered as a cycle. Okay, to produce a cycle you need to have at least 2 processes. Okay. Okay, the next thing would be, in a cycle, to constitute a reversible cycle we must remember that whatever the processes are constituting that cycle, the processes individually should be reversible. That means if 1 2 2 1 is a cycle, we must remember that to constitute a reversible cycle, 1 to 2 must be a reversible process and 2 to 1 must be a reversible process. Okay, that means to constitute a reversible cycle, the processes which are constituting it, the series of processes which are making this cycle must be reversible processes. That's the only condition which will make this total cycle reversible. Okay. Okay, the next thing would be thermodynamic equilibrium. Now what do we mean by thermodynamic equilibrium? In thermodynamic equilibrium, that is an equilibrium condition in which the system must not have any unbalanced potential or any driving force. Okay, so that's when we call that the system is in thermodynamic equilibrium. Now to have this equilibrium state, we need to focus on these three types of equilibriums. Okay, if we fulfill these three conditions, then we can say that our system is in thermodynamic equilibrium. The first one is thermal equilibrium. What do you mean by thermal equilibrium? Thermal equilibrium means that temperature at every point in the system must be same. In each and every point of the system, the temperature must be same, because we know that the temperature difference is the main reason for heat transfer. If there is any temperature difference between this point and this point, there must be a heat transfer, and if the heat transfer is going on, we cannot say that the system is in equilibrium. Okay, so thermodynamic equilibrium means thermal equilibrium means there must not be any difference in temperature in between any 2 points in a system. Okay, mechanical equilibrium. What do you mean by mechanical equilibrium? In mechanical equilibrium, what happens is it avoids the inequality of all those properties which may lead to a work transfer. Okay, suppose here is a property and here is a property. This difference of this property is going to give us a work transfer. So this mechanical equilibrium will take care of the equality of these properties. It will make all those properties equal which can give us a work transfer. Okay, so this will take care of this. Now what is chemical equilibrium? Chemical equilibrium will take care of those equality of those properties which is going to lead to a chemical reaction. Okay, this equilibrium is going to avoid all the chemical reaction that is going to happen due to an inequality of different properties. Okay, so in this equilibrium we will maintain the equality of these properties which can lead to a chemical reaction. Okay. Okay, the next thing we need to study is about gases. Now to understand gases very easily, we need to focus on the types of matters. If we understand matter, out of that matter which of the things are known as gases, we will know by this chart. Okay, now matter are of two types, solids and fluids. Now we all know the difference between solid and fluid, but we must know it in terms of engineering. Now in terms of engineering, what is going to be the difference between solid and fluid? In solid, what happens if these solids have a very definite or definite value of deformation under the action of shear force, and another thing is that this tries to gain its original position or original shape when the load is removed. Whereas in fluid, what happens, there is a infinite deformation under the action of shear force, and they don't even try to get into their original shape and size. Okay, now this solid is again divided into two parts, rigid and deformable. In rigid, what happens, whatever the load you give, suppose this is a block and there this here I have shown two molecules, and let the distance between two molecules is x. Now I have given some load in terms of moment. Now in rigid body, the deformation will not take place. Okay, in the final state, what will happen, the intermolecular distance between these will remain the same value of x. Okay, that means is rigid body, the intermolecular distance doesn't change because they do not deform. Whereas in deformable, what happens, if I apply the load in terms of moment, this will try to bend, and this will, if this try to bend, the molecules above the neutral axis will try to go apart. Due to the bending, these molecules above the neutral axis will try to go apart and form a new distance, that is x dash, which is larger than this one. That means in deformable, what happens, the relative position of the molecules changes when the load is applied, and when the load is removed, it tries to gain back its original position. Okay, now again fluid. In fluid, there are of two types, one is liquid and one is gases. Now what is the difference between liquid and gases? In liquid, what happens, the liquid has a certain surface, a liquid has a free surface, whereas gases don't have a free surface. But in that case, both these take the shape of a container, but whatever container they are in, a liquid always have a free surface. Due to the surface tension, they always have a free surface, but gases don't have a free surface. Now these gases are divided into two parts, real and ideal. Ideal is a theoretical consideration. Ideal gases are theoretical considerations only. These gases doesn't exist, but real somehow to some extent matches to this ideal gas, but they exist in real life, whereas this ideal gas don't exist in real life. This is taken for theoretical consideration only. Okay. Okay, the next thing we need to know is ideal gas. Now what do you mean by ideal gas? Ideal gas is the gas which in each temperature and pressure is going to follow the ideal gas equation. Okay, in every temperature and pressure, whichever the gas is going to follow this equation is known as ideal gas equation. Is going to follow this equation is known as ideal gas. Okay, now here in this equation, these notations have different meanings, like P is equals to absolute pressure. What is absolute pressure? Absolute pressure is atmospheric pressure plus gauge pressure. Gauge pressure means whatever the pressure your instrument is showing, okay, if you add the atmospheric pressure to it, then you are going to get absolute pressure. Okay, V is the volume meter cube, we all know. M is going to be the mass in kg. R is going to be the characteristic gas constant in kilojoule per kg Kelvin. Okay, and T is going to be the absolute temperature whose unit is going to be K, that means Kelvin. Okay, now some of you might get confused by this equation PV equals to MRT, because in some 11th standard chemistry or somewhere you might have read that the ideal gas equation is PV equals to nRT. Okay, here N means the number of molecules, here M means the mass kg. Okay, and another confusion you might have is that in some places you have taken R value as 0.287 for gas, and in some places you have taken R value is equals to 8.314. Now what is the difference between these R and these R? What is the difference between the equations of this equation and this equation? This all confusion is going to be erased if you listen to this video carefully. Okay, now what happens is, according to some equation, you might get the total number of molecules, that is this N. Now somewhere you might have read that total number of molecules is going to be total mass of gas divided by mass of one individual molecule. Okay, suppose M is the total number of mass, that is this M. Okay, M is the total number of mass, and if you divide this by the number of each and every molecule, that is capital M, then you are going to get what is the total number of molecules present here. Okay, this is very simple arithmetic. Total mass divided by total mass by the mass of individual molecule will give you the total number of molecules. Okay, now what happens is, from this equation we can replace small m by n into m. Okay, now if you replace it here, P into V equals to if you replace m, then it will be n into m into r into T. Okay, now according to Avogadro hypothesis, what he has said that for a certain temperature and pressure, all the gases will be having same number of molecules. Okay, in normal temperature and pressure he has given the number of molecules as 6.026 into 10 to the power 23, which is known as Avogadro number. But for each and every temperature and pressure, there is going to be a certain number of molecules which is going to be constant according to Avogadro. Now what happens is, he has taken pressure constant, temperature constant, so volume will be automatically constant. Okay, now he has again said that for certain temperature and pressure, number of molecules is also going to be constant, that means N is also constant. So to satisfy this equation, M into R is also going to be constant. Okay, now this M into R is a constant which is known as Ru. Okay, now this R is known as characteristic gas constant, and this Ru is known as universal gas constant. Whatever the value I have showed, that you have taken R value as 0.287, this is for this R. Okay, this will change from gas to gas. This R value is going to change from gas to gas. This is characteristic gas equation. If you take oxygen, then this R value will be different. If you take another gas, suppose nitrogen, then this R is going to be different. But this Ru is always going to be constant for any gases you take. For every gases you take, this Ru value is going to be at 8.314 kilojoule per kilomole Kelvin. Okay, and this M is also different. For oxygen, this M is going to be 16. Okay, for hydrogen H2 it is going to be 2. Okay, so for every gases this M is different, this R is different for every gas, but this product is always going to be constant, which is known as universal gas constant. And that is the way how we get this equation PV equals to N into Ru into T. In some places they also write it as N into R dash into T. Okay, now this is the difference between PV into MRT and PV into NRT. Okay, I hope you understood this. So this RU is going to be constant for every, and this value is going to be 8.314 kilojoule per kg, kilojoule per kilomole Kelvin. Okay. Now if you are to find any R value, suppose we need to find this R value of air, you can always take RU as our 8.314. Okay. Now suppose I need to find R of air, this characteristic gas constant of air, R air I need to find. So I can easily write this as, if we consider this equation, then we can easily write it as RU by M of air. We can write it. Okay. Now molecular experimental value of molecular weight of air is going to be 29 always. Okay. And we have 8.314 as the RU value. Now from this, if we take this, then we can get the value characteristic constant value of air, now which is going to be 0.287 kilojoule per kg Kelvin. This equation is going to be kilojoule per kg Kelvin. Now this is the procedure how we find R value for a single gas. That is, for oxygen we can find it, for hydrogen we can find it. For oxygen in place of M it will come 16. Okay, for hydrogen it will come 2. Okay, in this way we can find the characteristic gas constant for each and every gas whatever we take. Okay, now I think you have got the difference between PV equals to MRT and PV equals to nRT, and what is the difference between R equals to 0.287 and R equals to 8.314. Okay. Okay, the next thing would be mixture of gases. Now first of all, let us suppose that there is a system, and in this system there are n number of gases. Okay, from starting from number, if we number these gases from starting from 1, 2, 3, there are n number of gases. So we have listed down some of the properties for each of the gases. So first of all, if we number one of the gases as number 1, then we have listed down these properties like mass m1, volume v1, temperature T1, pressure P1, number of molecules n1, characteristic gas constant of that particular gas as R1, molecular weight as m1. Like this way we have listed down for number 2 gases, and in this way we have listed down all the properties of n number of gases. Okay. Now in this, from this mixture, what we get, that the total mass of the system is going to be the mass of individual gases. That means summation of m, that means total mass of the gas is going to be the summation of mass of the first gas plus mass of the second gas plus dot 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 up to n number of gases. We will add up all the masses to get the total mass. Now in volume, what happens? We all know that however small amount of volume is there of the gas, it will take up the whole volume and expand itself. Okay, so even if it is in mixture, if there are n number of gases, these individual gases will also take up the whole volume to occupy this, to occupy the container. Okay, so that is the reason why each of the mass is going to be going to occupy the same amount of volume, which is going to be the volume of the container. Okay, so that is why the volume is going to be same for all the gases. V equals to V1 equals to V2 equals to V3 equals to V4 equals to up to n number of gases. The volume would be same, because even if it's in mixture, it will occupy the volume of the container. In same way, temperature is also going to be same for all the gases. It is not like that we will add up all the temperatures. Okay, it is not like that. So the last final temperature of the system is going to be equal for all the gases. And according to Dalton's law, we know that the total pressure of the gas will be equal to the sum of the individual gases. Okay, this is the concept of partial pressure. So if there is one gas, if this gas, number 1 gas is having pressure P1 and number 2 having P2, in this way n number of pressures will be there, then the total pressure of that system will be going to be the addition of all this pressure that is given by our Dalton. Okay. Now if we write all the equations of the ideal gases, for each of the gases, if we write the ideal gas equation, we can write that P1 V1 equals to N1 R dash T. We all know that PV equals to M R T and PV equals to M R dash T. R dash is the universal gas constant. So if we write in this way, P1 V1 equals to N1 R T1, P2 V2 equals to N2 R dash T2. In this way we have written equations for n number of equations. Okay. Now if we, as the volume is going to be same, we can take the volume equals to V here. because volume of all the gases is going to be same, and the pressure we will add up all the pressures, okay, which will give us a final pressure of P. Now in this column again temperature is same and universal gas constant is also going to be same. So if we take R dash and T common, we will get the addition of N1 N2. This is number of molecules of gas 1, number of molecules of gas 2, number of molecules of gas 3. In this way we will get N number of molecules, and we will add it up to here taking R dash and T common. And if we take this equation, we will see that all the summation of the pressures according to the Dalton's law is going to give us P, which we have written here. V is same as the previous one, equals to, now this N1 plus N2 plus N3 is going to consist summation of N, total summation of N, and R dash and T are common. Okay, so we can derive this thing out of the mixture of gases. Now we will see mole fraction. Okay, the next thing would be mole fraction. Now what is a mole fraction? Mole fraction is nothing but the ratio of the number of molecules of a particular gas divided by whole number of molecules in that mixture of gases. Okay, for example, if I take an individual gas, we need to find the mole fraction of an individual gas, then we'll say that it is the ratio of number of molecules of that gas divided by total number of molecules of all the gases in the mixture. Okay, so basically what mole fraction means, it means the what fraction of number of molecules is going to constitute by this particular gas out of all the gases. Okay, so this will be given by the number of molecules of that individual gas by the whole number of molecules in that mixture of gases. Okay, so we can write it like this. So if we take from the previous diagram, if we take the first gas, then the mole fraction of it would be N1 by the number of molecules of all the gases. Okay, so in X2 will be again the number of molecules of the gas number 2 divided by number of molecules of all the gases in the mixture. So in this way, if we add X1 plus X2 dot dot dot, dot up to N, if we add, it will give us the value of 1, because if we add this one plus this one plus this one, then this thing will come as LCM, and in the numerator we will get N1 plus N2 plus N3 plus dot dot dot, dot up to N we get. So these two denominator and numerator is going to cancel out, and we will get 1. Okay, so to better understand this, let us make a system, and there are suppose 4 number of gases: oxygen, nitrogen, carbon dioxide and carbon monoxide, suppose. Okay, now if you need to find what is the mole fraction of oxygen, first of all you need to get what is the number of molecules of oxygen is present in this system. So if NO2 will give us the number of molecules of oxygen in this system, then the mole fraction will be given by the number of molecules divided by summation of all the molecules in the gases, that is NO2 plus NN2 plus NCO2 plus NCO. Okay, so if we divide the number of molecules of gases of oxygen, number of molecules of oxygen by all the summation of all the number of molecules of all the gases present in the mixture, then this will give us the mole fraction. Okay, now this is one of the equation which we have derived in the previous diagram. Okay, so this is the ideal gas equation for the whole mixture of the gases, and for a particular gas, for an individual gas, if I write the ideal gas equation, then this will be like this: Pi Vi equals to Ni RT. I for individual, for a particular individual gas, if I write, then this will be Pi Vi equals to Ni R dash T. Okay, and for the mixture this will be this. Now if we divide equation 1 by equation 2, R will cancel out, TT will cancel out, here V and Vi will be cancelling out, because Vi and V are going to be same. Okay, so after dividing we get Pi, that is the partial pressure of that individual gas, divided by the total pressure, will give us the ratio of number of molecules of individual gas divided by total number of molecules in the mixture. Okay, now this thing we know as mole fraction. Okay, mole fraction of that particular gas. Okay, now if we cross multiplicate, then this will give us Pi equals to P into Xi. So from this whole thing we get that if I want to find out the partial pressure of an individual gas then you need to divide the whole pressure, that is total pressure, will multiply with the mole fraction of that particular gas. Okay, suppose from this mixture I need to find what is the partial pressure of oxygen from the total pressure. Suppose the total pressure is P and the partial pressure of oxygen is going to be PO2. So if I divide this pressure with the mole fraction of oxygen, then we will find the partial pressure of oxygen. That means to find out the partial pressure of oxygen, we will multiply the total pressure with the mole fraction of oxygen. Okay. In the next board we will see a numerical based on this. Okay. Okay, about the previous discussion, there is a small problem through which we can understand the partial pressure or the mole fraction very well. Okay. Now in this question, what they have said that in a container there are two gases, 3 kilomole of nitrogen, 7 kilomole of carbon dioxide. Okay, and the total pressure of the mixture is given as 300 kilopascal, and find the partial pressure of N2. Now what they have given, 3 kilomole of N2 means they have given the number of molecules of N2. Okay, 3 kilomole, that means 3000. Okay, now they have given carbon dioxide as number of moles of carbon dioxide as 7. That means N carbon dioxide is going to be 7000. Okay, now they have given that the total pressure of the mixture is, that means the total pressure they have given as 300 kilopascal. Okay, now suppose there is a system, there are two gases, N2 and CO2. The number of molecules of N2 given is 3000 and number of molecules of CO2 is given as 7000. Now we need to find the partial pressure of N2. Okay, we need to find the partial pressure of N2. That means from the previous diagram and previous derivation, what we have found out that if we want to find the partial pressure of a particular gas, that means here in this case we need to find the partial pressure of nitrogen, then we will need to divide the mole fraction of that particular gas with the total pressure, then we will find the partial pressure. Now what is going to be Xn2 here? Now as we have said, the mole fraction is going to be the ratio of number of molecules of that particular gas. That means here number of moles of N2 is 3000 divided by total number of molecules in that gas. Now what will be the total number of molecules in that gas? That will be summation of number of molecules of N2 and summation of number of molecules of CO2. Now here these are given as 3000 and 7000. If we add 3000 and 7000, we are going to get 10,000. Okay. Now we need to multiply it with the total pressure. The total pressure is given as 300 kilopascal. Okay. Now you cancel out 3 zeros and 3 zeros and 1 with this 0. Now we will get, what will we get? We will get 90 kilopascal. Okay. So this is the thing we need to find. Then now what does it mean? It means that the partial pressure of nitrogen in that mixture is going to be 90 kilopascal. Okay. And the partial pressure of that carbon dioxide in this mixture is going to be 300 minus 90, because the summation gives the total pressure. So one individual is 90, then the other will be obviously 210 kilopascal. Okay. So in this way we find the partial pressure by multiplying the total pressure with the mole fraction. Okay. Okay, the next thing we'll discuss is equivalent gas constant, and this gas constant is going to be characteristic gas constant. This is not going to be the universal gas constant. Okay, that means in a mixture there will be several number of gases, and several number of gases will be having several number of characteristic gas constant. Okay, now in the whole mixture, what will be the equivalent gas constant? These are we are going to derive. That means suppose if we take air, now air is a mixture of many other gases. Okay, from there what we get, the characteristic gas constant of air is given as 0.287 kilojoule per kg kilogram. Okay, now this is an equivalent gas constant for all the mixtures that air is having. All the mixture of gases the air is having, this R value is the equivalent characteristic gas constant of the whole mixture. But individually, if we take individually each and every gases that is constituted by air, we will find that each and every gas is having their individual characteristic gas constant. Likewise, we are going to find that what will be the equivalent gas constant for a mixture. Okay, now in mixture there are several number of gases, so we have written down the ideal gas equation for each of the gases present in the mixture. Okay, so here we have taken M1 R1 into T. If we take N, then there will be equivalent universal gas constant, but as we have taken M, it will be characteristic gas constant according to our previous discussions. Okay, so we have written down up to n number of gases. So what will we find if we add again V1, V2, V3 is going to be same. So V will be common, we will add up all the partial pressures. Okay, now in equal we will see that R1 is different for different gases, R2 is also different for different gases. Similarly M is also different for different gas, M2 is also different for different gas. Likewise we find only T is common here. If we had taken N1 R dash T, we will have taken common R dash into T, because R dash is constant for every gases, but R, that is the characteristic gas constant, is not common for every gases. That's why we can only take T as common. R is going to be inside the bracket. Okay, so M1 R1, we can take M1 R1 plus M2 R2 plus dot 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 up to somewhere. Now if we take the whole ideal gas equation for the complete mixture of gases, we will find a equation something like this. P is going to be the total pressure volume into summation of M into R equivalent, that is R equivalent of the complete mixture into T. Now this is the equation what we could have get if we would have considered it in a whole, but in this case we have taken first partially, then we have written what we could have got. Okay, now from equation 1 and equation 2, if we compare what we get, this summation is always going to be, will always give us P. Okay, so this thing is going to be same, P and V is going to be same, T is also going to be same. The only only comparison we will find that this summation and summation of M by M into RE is going to be different here. So to be equal, to be real, these two equations must be equal. So to be equal, we must take that these two things is going to be same as this one. Okay, that means we can write summation of M into RE is going to be equal to M1 R1 plus M2 R2 plus dot 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 dots up to M and Rn. Okay, so from here what you can get, R equivalent is going to be M1 R1 plus M2 R2 plus dot 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 up by summation of M. Okay, now this is going to be a formula to find out the equivalent characteristic gas constant. Okay, so I will say again one more time what we have done here. We have taken the individual ideal gas equation for all the individual gas which have constituted the mixture. That means in the mixture whatever gases are there, we have taken the ideal gas equation for all these gases. Okay, after that we have found out this equation. Now for a complete mixture, if we find the ideal gas equation, then we would have find something like this. That means if we got a characteristic gas constant for the mixture, that would be RE, total mass would be the summation of all the masses, T. Okay, that means for a whole we have written the equation, and we have got another equation by adding up the ideal gas equation for all the individual gases. Now after that we have compared both these equations. So from here PV is going to be same, T is going to be same. The only different thing is going to be del M into RE and these additions. Now if we equate this from this equation, we can easily get the value of RE.